Good morning, boys and girls. In our last section, we talked about infinite limits, the limit as we approach a vertical asymptote and how that would give us, we could describe that with our limits using infinity or negative infinity. Today, we're going to discuss limits at infinity, which has a very similar sounding name, but is a different. This is the limit as x approaches infinity or the limit as x approaches negative infinity. Okay? So slightly different, but the names are similar, so I do think they get confused sometimes. We're going to kind of quickly look at this graphically here. I have two graphs for us. If we look at the graph on the left-hand side over here, let me change my color real fast, sorry about that. If I look at the limit as x approaches infinity, if we call this f of x, as I go to infinity, this graph is going up and up forever and ever and ever. Therefore, this is not approaching a singular y value, and therefore there is no limit here, so we would say that this limit does not exist. Okay? Same thing on the left-hand side, if the limit as x approaches negative infinity, because this is going up, or if it was going like down forever and ever and ever, it is not, again, approaching a singular y value, so again, in that case, the limit would not exist. The graph on the right, however, if we look at this one, now, as I go to infinity, we are approaching I'm approaching a horizontal asymptote. And now, as I go to infinity, this is going to -1. It's approaching and getting closer and closer to -1. Because this is approaching a singular y value, we could say that this limit does exist, and as I go to infinity, the function is going to -1. So just like we described the behavior near vertical asymptotes, we can use limits to describe the behavior near horizontal asymptotes, and that's what limits at infinity or limits at negative infinity are. Okay? In this case here, the limit as x approaches negative infinity, because this one is going up and again going on forever and ever and ever, again that would be does not exist. Okay? So we're going to get limits at infinity or limits at negative infinity when we approach horizontal asymptotes. So we might want to go back and let's review our rules for horizontal asymptotes. Okay, so here we go. Here are our three rules to find the horizontal asymptote of a function, right? We said we have a fraction going on, and if you look at the degree of the top of the fraction versus the degree of the bottom fraction. If the degree of the top was less than the degree of the bottom, then you had a horizontal asymptote at y equals 0. If the degree of the top equaled the degree of the bottom, you had a horizontal asymptote at y equals a over b, where a and b were the leading coefficients of the polynomial on the top and the bottom. And then we had, if the degree of the top was greater than the bottom, then there would be no horizontal asymptote. And you may remember, and we're going to not get that into it here, but you may remember from trig pre-calc algebra 2, that if the degree of the top was 1 more than the bottom, then you have a slant asymptote. And we said you could go ahead and say synthetically divide or divide using long division to write the equation of that slant asymptote. We're not going to get that crazy here. I just wanted to remind you of that fact. All right? So these come in very handy. These rules come in handy when we're trying to evaluate limits at infinity and limits at negative infinity, since, again, those occur at horizontal asymptotes. All right, let's do some examples with this, and let's think about how we can maybe even solve some of these things analytically. Okay, here's our first example. I know we said, generally, when we're looking at the limit as x approaches infinity, the first thing you want to be thinking about is horizontal asymptotes, because that's, again, where those things are going to occur. But the first problem I gave you here is not in the form where we can find horizontal asymptotes. I guess if you really wanted to, you could go ahead and add those fractions together, the common denominator, and put everything together, and then find your horizontal asymptote. But this is one we can approach analytically as well. And I can kind of just think about what's happening. We said when you evaluate a limit, you kind of want to plug in first direct substitution. I can't, I'm going to think about this. Again, I'm writing down what I'm thinking about. Okay. This is not necessarily good math notation, but if I just think about what's going on here. If I have 5 plus 1 over infinity plus 10 over infinity squared, if I take 1 divided by a very, very big number, right? The bigger the number I divide by, the smaller this fraction here is going to get, right? If I divide 1 by a really, really big number, or really any constant by a really big number, the smaller that's going to get. So as I divide by infinity, this is going to go to 0. And then I guess the same thing over here happens as well. 10 divided by infinity squared. Infinity squared is even a bigger infinity. So, 10 divided by a really, really huge number is also going to go to 0. So in this case, then I really would end up, as I go to infinity, 5 plus 0 plus 0, or my horizontal asymptote would be at 5, I could say. That kind of, again, could be a proof of the horizontal asymptote. Or the limit as x approaches infinity is 5. Okay, next example. The limit as x approaches negative infinity of 3x to the 11th power. So kind of going back to the last one, the first thing we're going to want to do is try a little direct substitution, or at least, again, this is what I'm thinking about in my head. Again, we can't really plug in infinities, because infinity is not a number, but I want to think about that. If I were to plug in negative infinity in my head, if I took negative infinity to the 11th power, really what I just care about is my power and the sign of what's going on here. If I took negative infinity and raised it to the 11th power, any negative number we've said to an odd power is going to be negative. So that would basically just go to negative infinity. And now 3 times negative infinity is still negative infinity. So this is going to go to negative infinity, we could say, and let people that it's going down forever and ever. Or again, we could say that it does not exist. Again, we're going to try to describe things just like yesterday with, the infinities and negative infinities. I'm going to say try to write that answer down right there. But you also, again, might see does not exist. Either one of those things is okay. Okay, here's our next example. The limit as x approaches infinity of 4x over 20x plus 1. Alright, here's some other analytical things we can do with limits as we approach infinity, and other ways we can think about this. If I want to evaluate this limit, okay, if I've got 4 times infinity over 20 times infinity plus 1, if I'm doing 20 times infinity plus 1, is that plus 1 really doing anything? I mean, I'm already getting so big so fast. We say that when you have something like this, the plus 1 is not really going to affect what's going on, since I'm going to infinity. So I can kind of simplify this in my head and think about just 4x over 20x. And look at the limit as I approach that. And if I'm looking at that, the limit as x approaches infinity, then my x would go ahead and cancel off. They're gone, and I'm left with just 4 over 20, or 5. Now, if I think about what we just did right there, let's do this. Sorry, kind of getting ahead of myself a little bit. Let's do the one on the right first, and then I'll talk about what I was going to talk about. If I do the same thing with the limit as x approaches negative infinity, the same thing's going to happen because we're going to negative infinity. This plus 1's not going to care so much affect what's happening. So I'm going to look at the limit as x approaches negative infinity of 4x over 20x. And again, those x's are just going to cancel off. And so I'm left with 4 over 20, or again, in this case, I'd be left with 5. Now, this is why, when I'm dealing with limits as x approaches infinity or x approaches negative infinity, I tend to think about my horizontal asymptote rules. We said that's when we're going to get these. And if I go back to this original problem and I think about this, in this case, the degree of the top is 1, the degree of the bottom is 1, so I'm going to look at leading coefficients, which is the 4 over 20 part. And so, again, I get 5. Either way, I'm thinking about this either through horizontal asymptotes or through analytically evaluating my limit. I'm going to get the same answer. This is actually the proof, though, mathematically speaking, for those rules that we came up with in the first place, for those case 1, case 2, case 3, for our horizontal asymptote rules. Like in the past, we just gave those to you and said, hey, here are the 3 rules for horizontal asymptotes. This is actually where they come from and where they were actually proven is through the use of limits. So now I've kind of showed you how you could get there in the first place, and I think that's kind of cool. Okay, so let's apply that same analytical idea to this problem here. The limit as x approaches infinity, or the limit as x approaches negative infinity, of 3x squared minus 7 over x squared plus 5x. Okay, so for this one, again, if I'm going to plug in infinity to this thing, if I subtract 7 from this, it's really not going to matter, right? By the time I take infinity and square it, who cares about minusing 7? And even more so, if I'm going to take infinity and square it, if I go 5 times infinity, this infinity squared is going to grow so much faster than the 5 times infinity that we can ignore this 5x and back even. So like that's when we're dealing with these things, you can ignore all the stuff in the back. We just care about what's happening with the greatest exponent. And so in this case, I get 3x squared over x squared, and now the x squareds cancel off, and so we're left with just 3. Going back to our horizontal asymptote rules, that same thing again, if I look at the degree of the top and the degree of the bottom, they're the same. So I'm just going to look at leading coefficients. Hey, 3 over 1. So this is going to go to 3. Okay, that's where that rule comes from. That's why I only deal with leading coefficients when I'm looking at this. It's because all the other stuff, as I go to infinity, it basically doesn't matter and it ends up dying off. Same thing as I go to negative infinity here. Okay, in this case, as I go to negative infinity, that negative 7 is not going to matter. The plus 5x is not going to matter. And so again, in the same case, I would go here, and I'd be at 3x squared over x squared. The x squareds cancel off, and we're at 3. Okay? So as I go to the right, forever and ever, it's approaching 3 in this graph. As I go to the left, forever and ever, it's approaching that same horizontal asymptote, and it's 3. I'm going to say be very careful. We're going to get to ones here pretty soon. I mean, most of the graphs you have dealt with before in your lives, if I have a horizontal asymptote, I approach, that value, and as I go to the left, I approach the same value. That doesn't always happen. We can have multiple horizontal asymptotes, and we can actually get different values when I go to the right and to the left. We're going to see an example of that in a second here, but be aware, watch out for that. Okay, here we go. One more real quick example of this. The limit as x approaches infinity of x to the 4th plus 7 over x to the 5th plus x squared minus x. So we said, as we're going to infinity, all the stuff at the back doesn't matter. I really just care about the greatest powers. I'm really just going to think about x to the 4th over x to the 5th. In this case, then, I can reduce those things. And so I get 1 over x, or at least I'm thinking about that in my head. And now as if I do the limit as x approaches infinity of 1 over x, we said 1 over a really big number is going to go to 0. So this would be 0. Okay? Again, approaching this a different way, if I just approach this using the horizontal asymptote idea, if the degree of the top is less than the degree of the bottom, we know we have a horizontal asymptote at y equals 0, so this limit would be 0. Okay? Quick and easy, just like that. We got one more example, and then we'll be done for today. All right, here we go. Number 6. I'm going to say, whenever you see a limit going to infinity with a square root in it, watch out. These are the ones that are kind of weird, where you don't just get one answer to the right and the same one to the left. You're going to get 2 different answers, and here's why. We said if we're taking the limit as x approaches infinity, we can get rid of all the stuff in the back, right? The plus 1s don't matter. So this basically becomes the square root of x squared over 2x. Now, if I'm looking at that limit, I could actually go and take the square root of x squared, and so that would be x over 2x. And now, as I reduce that, I would get 1/2. Okay? So this limit would be 1/2, or there's a horizontal asymptote as I go to infinity of 1/2. Doing to negative infinity, my work turns out very similar to this. I get the square root of x squared over 2x. I don't have to worry about the plus 1s. I take the square root of that. However, what I neglected to mention was whenever you take the square root of a number, right? The square root of 9 is always 3. It's not negative 3. Whenever you take the square root of a number, you always get a positive value. So really what I should have done over here was put an absolute value on that. And so, like, when I do infinity, it didn't really matter because infinity was positive. But now when I plug in negative infinity, on top I would have, like, the positive infinity, and on the bottom I'd have a negative infinity. So in this case here, it's really going to go to negative 1/2. Okay? So that's where I'm going to get 2 different asymptotes. To the right, there's a horizontal asymptote at 1/2, and then to the left, there's a horizontal asymptote at negative 1/2, all because of this absolute value related to the square root. Thank you, boys and girls. If you got questions, as always, come ask me. See you later. Have a nice day.